The concept of gravitational time dilation, a real elapsed time difference between two events as observed from diverging distances from a large gravitational mass, was originally introduced by Albert Einstein. According to this principle, the closer a clock is to a gravitational source, lower gravitational potential, the slower time runs as the clock moves away from the gravitational source, essentially raising the gravitational potential. Time speeds up. This incrementally complex part of general relativity has been repeatedly validated through tests and experimentation concerning precise measurements of specific atomic clocks placed at varying altitudes, hence fluctuating gravitational potentials, which eventually display divergent timescale. These Earth-based trials typically yield exceptionally minor variations, often recorded in nanoseconds. Interestingly, in relation to Earth's age that spans billions of years, the core is technically younger than its surface by about 2.5 years. Demonstration of more substantial effects would demand distances far beyond Earth or a much larger and denser gravitational source. Einstein first posited gravitational time dilation as a secondary effect of special relativity concerning accelerated frames of reference. In a broader context of general relativity, it manifests as variances in proper time passages at different positions, dictated by a metric tensor of spacetime. The Pound-Rebka experiment in 1959 first affirmed the existence of gravitational time dilation. Subsequently, this theory was refined further by Gravity Probe A and other experiments. On a closely related note, gravitational redshift impacts a body's emitted light frequency when positioned closer to a gravitating body. Gravitational time dilation causes the light's frequency to seem slower and thus redshifted. Put simply, clocks far from massive bodies or in higher gravitational potentials run relatively quickly, and vice versa. For instance, considering Earth's lifespan of 4.6 billion years, a clock at an altitude of 9,000 meters, such as the one at the peak of Mount Everest, could be roughly 39 hours ahead of a sea-level clock. From the perspective of general relativity, gravitation and acceleration are undistinguishable, rendering gravitational mass and inertial mass equal, and simultaneously deeming all accelerated frames of reference physically equivalent to an equivalent strength gravitational field. The enactment of gravitational time dilation is experienced by observers in varying reference frames or gravitational fields. The time frame refers to a vertical line of respective observers, each undergoing a distinct g-force along the line. Gravitational time dilation is a prominent concept of relativity. It profoundly contributes to our understanding of the universe, gravity, and time. The formula presented delves into the concept of time as experienced by a close observer within the gravitational field of a massive sphere, as opposed to a distant observer far from the gravitational influence. This concept operates under the notion of Schwarzschild coordinates, a system where a clock at an infinite distance from the sphere ticks normally, while closer clocks show a slower rate. The formula paints a scenario where, barring rotation effects, a clock on Earth's surface inside its gravitational well would register about 0.219 less seconds over a year compared to a distant observer's clock. Comparatively, a clock based on the Sun's surface would fall short by about 664 seconds yearly. In Schwarzschild metrics, objects under free fall can have circular orbits beyond the extensive photon sphere, radius. The initial formula describes the resting clock, while the subsequent one determines the relativistic time dilation for a clock in a circular orbit. According to the general relativity theory, gravitational time dilation is synonymous with an accelerated reference frame. Furthermore, all identical physical phenomena experience the same time dilation according to relativity theory's equivalence principle. The speed of light in a region is always considered c by observers present there. This means each infinitesimal space-time region can have its own time, and the light speed according to the region's time is always c. It applies even if no observer occupies the given region. Interesting to note here is that photons traveling from Earth, bending near the Sun, journeying to Venus, and then returning back to Earth along a similar path will measure a time delay. Nonetheless, the constant speed of light theory remains unbroken, as any observer measuring photon speed in their area will still find it to be c. However, our observation of light traveling finite distances near the Sun will differ from some. Suppose an observer tracks the light in a remote location, which intercepts a time-dilated observer close to a massive body. The light and that observer will both exhibit a slower time clock than other light traveling towards the first observer at c. If the distant light also reaches the first observer, they will also measure it at c. This narrative boils down to the exploration and validation of gravitational time dilation, a time-honored concept that is immutable, indicating no movement terms. Noether's theorem plays a crucial role in establishing this concept, as it applies to objects dropping freely into a figurative well from infinity. Conservation of specific quantities emerges from the time invariance of the metric, or in terms adjusted to the local time dilation. Essentially, acquired speed-induced time dilation, gauged at the descendant body's location, is proportional to the gravitational time dilation within the well the body descended into. In broader applications, one concludes, maintaining similar metric presumptions, that the comparative gravitational time dilation between 2 points aligns with the velocity-induced time dilation necessary to traverse from the lower to the upper point. Empirical evidence of gravitational time dilation is seen through experiments such as the Haveli-Keating test, which involved atomic clocks on planes, which ticked faster than those on the ground. This discrepancy is noticeable enough that the GPS satellites must adjust their clocks accordingly. Remarkably, in laboratory conditions, the time dilation influenced by height differences less than a meter has been confirmed. Gravitational time dilation reveals itself as gravitational redshift, verified by the Pound-Rebka test and observing the spectra of the white dwarf, Sirius B. Further validations come from experiments involving time signals transmitted to and received from the Viking 1 Mars lander.